let's start.
Is it time to turn that in?
He hasn't asked for me.
So did we get into evaluation of damping last time, or maybe it was in the next class? Maybe I didn't know. So let's summarize then what we've done. We've been talking about free vibration of damped systems, right? Like the undamped systems, if you can summarize everything we did, what we really got out of that, which was really a fundamental topic, was we understood what is natural frequency, which is one of the most important inherent dynamic characteristics of the system. And we also learned how to set up the model, the single degree of freedom system model using various different techniques. Those were really the two important things that we got out of that. In free vibration of damped system, as I said before, we definitely, of course, looked at how that single degree of freedom system looked like, but we introduced a new element, which is also a dynamic characteristic of the system, which is damping ratio. So we learned how to set up the equation of motion by just, again, using it, whether it's free body diagram or whatnot. But most importantly, we really learned this new dynamic, this new element, which we hadn't talked about, which is the damping ratio. And damping ratio, in fact, is also an inherent characteristic of a dynamic system. So it is important to see, like the natural frequency that we could measure it, or analytically derive it, how we can measure this damping ratio. And that's another application of the free vibration of damped systems. So if you have a free vibration response of a damped system, one way to measure the damping ratio is actually from that response, especially for those cases that the system is underdamped, which is a vast majority of mechanical or structural or aerospace or marine structures, any structure. Most of the structures, even human body organs, whatnot, they're all mostly underdamped. So this is a typical response, in fact, of an underdamped system, as we've seen, right? Let's see how we do that. Let's say you can plot the response of an underdamped system, okay? Free vibration. You've done that. Actually, in your project, you did it, right? You had an underdamped system, or you assumed that actually it was undamped, but in reality it's underdamped. And you measured it, right? So you know how to plot this. So now let's recall, we look at two consecutive amplitude of the same sign. The distance between the two, as we know, defines the period of that oscillation, right? And this is, of course, the amplitude. You remember the amplitude was an exponentially decaying function, okay, described by this. Let's say you can measure the amplitude of two consecutive peaks, okay? I call this U sub n and U n plus 1. In other words, you measure this at some arbitrary time, and this is at a time one period after that. Okay? What we want to demonstrate is that as long as you can make these measurements, you can actually find the damping ratio in the system, or measure the damping ratio in the system. Let's see how. First of all, a few things. Remember, we know that the damped frequency was what? 1 minus zeta squared natural frequency, right? the period is what? Period of a system is what? Is 2 pi over the frequency. So the natural period, I show it that way, would be this. So if you substitute these into that equation, you can get what? You can get 2 pi over, in other words, I will substitute for this 2d is equal to, okay, 1 minus zeta squared would be 2 pi over t0. These two cancel out, so you get the relationship between the natural period and the damped period. And we'll see why we need that. So we have this, now we have this, okay? So now let's look at these two, and what I will do, I will look at the ratio of these two. In other words, I will write down the ratio of un plus 1 over un, okay? The amplitude is this, right? At any time. So at Tn plus 1, I have e to the minus zeta omega n at Tn plus 1, and here you have e to the minus zeta omega n times Tn. But as I said, Tn plus 1 is actually Tn plus 1 period. So I just substitute that in there. So I will get e to the minus zeta omega n times Tn plus Td. Here I have e to the minus zeta omega n Tn, right? This is the product of e to the minus zeta omega n Tn, e to the minus zeta omega n Td. So this part and this part actually cancel out. So what you will get, you get e to the minus zeta omega n Td. So if you now substitute for that in there, what you get, given that Td, right, is 2 pi over omega d, right? And of course, omega n is omega d divided by 1 minus zeta squared. I will substitute these in here, and what you get is delta would be e to the minus zeta omega d divided by 1 minus zeta squared times 2 pi over omega d and omega d cancel out. So delta becomes e to the minus zeta 2 pi over 1 minus zeta squared. What this relationship tells me, okay, or you can write it the other way, minus 2 pi times zeta, that as long as you can measure this ratio from this relationship, you can directly find zeta, right? But I don't like this. This is a little bit, maybe too complicated, or a little bit not a direct or easy relationship. So what I will do, I will take the logarithm, natural log, of both sides. And let's call the natural log of delta being this value. So you get this to be minus 2 pi zeta over 1 minus zeta squared. So as you can see then, by just measuring the ratio of those two and taking its logarithm, you can find then the damping ratio in the system. This can get actually even simpler, because for vast majority of the system, whether mechanical, structural, and whatnot, zeta is much smaller than 1. Let's say is 10%, 20%, even 30%. So you're talking about, let's say, 0.2 squared, which is what? 0.02. So it's very, very small compared with 1. So you can say this is almost equal to 1. Therefore, delta is actually minus 2 pi zeta. This is a very easy way to measure the damping ratio in a system, and that's one of the applications of the free vibration of damped systems that you can see. So this is one application or one aspect that we really were interested in understanding and studying, and the other aspect is how to set up the equation, solve for the response. So with that said, that's about it for the time being that we really want to know about underdamped, or I mean the free vibration of damped systems. We'll get to that more when it comes to the forced vibration. Any questions? If not, now we're going to actually start something more interesting. No questions? That is no way.
Sorry, I have a question.
Sure, no problem.
What is delta describing?
Delta is the ratio of two consecutive amplitudes in the response of a damped system. So you have plotted experimentally, like what you did in your project. If you could actually plot that function, you see that it looks like this.
So you just went from that delta to that delta?
Right, that's
Okay,
right, it's the
gotcha.
same, right, yes. Any other questions? Okay, now let's see where we are. As I promised, vibration, or in this course, we're going to study basically two broad topics. One was the free vibration of undamped and damped systems, and the forced vibration. We've completed that, right? We looked at both undamped and damped systems. Now we're done. Now we're going to look at this. So half the course. The only thing is this half is more involved than the first half. Okay? So we will then start again with undamped systems. The only thing is that here we just had one case, free vibration of, let's say, undamped system, and that is it. But in this case, when we say forced vibration, depending on the nature of the force, we may have different types of responses or quantities, attributes, and physical significance of the system that we are going to study. So the types of forcing functions that we consider are going to be either harmonic, periodic, or general. Even this general can be deterministic, like a blast load, impact load, earthquake excitation, or random. Of course, earthquake excitation is not a good example, but nevertheless, you can both consider that in form of a deterministic function or a random function, but this in itself is a different class. But a periodic, of course, vibration, which means something for us, is like this. Thanks to another, these French people made a lot of contributions, I tell you. Mr. Fourier, of course, thanks to him, we know that a periodic function can be, in fact, converted to a harmonic function. But we'll see all of these later. So for the time being, we're going to focus on harmonic excitation of undamped systems. In other words, mathematically speaking, or let's say physically speaking, you have a system like this that instead of freely vibrating, you subject that to a forcing function that is harmonic, sinusoidal, with a frequency omega and amplitude that I show that amplitude at F0 bar. So this is the system. Right? So you have a beam, you have this f of t, which looks like this. So that's what we're going to look at. So mathematically speaking, what we're dealing with is this. Remember from your differential equations that now this equation has basically, the solution consists of two parts. Homogeneous part, which we solved earlier, which is when the right-hand side is 0, and that's the homogeneous equation, plus a particular part, okay? And the solution, the total solution is the sum of the two. As we will see, although you may not appreciate it now, as we get to know more, we'll see why. This part, we call that transient, and this part we call steady state. The reason we call those names is that the left-hand side, even if you have an underdamped system, not just if free vibration, especially in the case of underdamped system, it dissipates with time, right? So it's transient, it disappears. You have an underdamped system, decays with time, right? However, this part depends on the action of the forcing function. If the forcing is there, you will have that vibration ongoing as long as the force is there. That's what we call that a steady state. But we'll see other reasons that we call those that way later. But let's start with the solution. Since you probably, some of you have not had Laplace transform, which I think is a good assumption, and those of you who haven't, who've had it, you may not like that. So let's use just a traditional approach, okay? In order to solve for the particular solution, which is what we want, you make the assumption that the particular solution is of this form. When the system is undamped, the frequency of this is the same as the frequency of the forcing function, so you need to find the amplitude. So what you do, you just substitute this back into this equation in order to, if this is the assumed solution, you substitute this back into that equation in order to find the unknown amplitude. So if you do that, that means you take m, u double dot of p plus k u of p is equal to f0 bar sine omega t. So if you do this, you take a second derivative of that, this is what it will become. It becomes, and you take the a factor a out, you get minus omega squared m plus k times sine omega t is equal to f0 sine omega t. So the amplitude, this should be the same as this, should be equal, these two are equal, so those two should be equal. That means the amplitude of this oscillation then would be f0 over minus omega squared m plus k. You can actually divide the numerator and denominator by k, so you can write this as f0 over k divided by, and if you divide this, it would become one, it would become like this, okay? It would become 1 minus omega squared over omega n squared, okay? Because if you divide this by k, it would become 1 minus omega squared m, right? But what is, well, I mean, if you divided by k, of course, right? So what is m over k is 1 over omega n squared. So that's what it becomes, okay? Let's call this ratio of omega over omega n as r. We call this frequency ratio, or the ratio of the forcing frequency over the natural frequency. So the amplitude then would take the form as f0 over k over 1 minus r squared. So with that said then, the steady state solution then, the steady state solution becomes what? f0 over k over 1 minus r squared sine omega t. We've done our job as far as solving this equation mathematically, so from the differential equation part concerned, we are done. However, we're talking about mechanical vibration. So more importantly, we really want to understand the physical significance of all these mathematical terms. So I would call studying these or understanding them and assessing them as observations, or let's say assessments, whatever. Yes?
So that's for the steady state solution?
That's for the steady state
Not the
solution.
particular?
No, well, good point. A steady state in particular is the same. So what I should have said is that the homogeneous part, we call this U sub t, the steady state part, or the particular solution, we actually call the U sub s. So as I was going through, unknowingly, I just quickly changed the notation without emphasizing it. Thank you for raising it. US means the particular solution, which is same as U sub t. Any other questions? Let's look at this and see what we have done, okay? Number one, easy. We see that the period of this oscillation, of this response, is the same period, or its frequency, of course, as that of the forcing function. Done. That's the first observation we made. The more we go actually in depth, it becomes more interesting. Observation number two is that, in fact, as we demonstrate, okay, we can actually see that for this particular response, right, if you said u at time, consider u at time equal to 0, that would be 0. But the velocity at time equal to 0, okay, is not 0, right? Take the derivative, okay, for the u, if you put t equal to 0, obviously this is 0, so the whole thing becomes 0. But for velocity, if you take the derivative, you have a cosine function. If you put time equal to 0, that'll be 1. So velocity is not 0. Okay. Observation number 3. This is the steady state response, but the complete response, as we know, consists of the sum of the two. The homogeneous response was what? Was, depending of course what form we use, I just write one of them, was this, A1 sine omega nt plus A2 cosine omega nt, right, plus F0 over K, 1 minus R squared sine omega t. This is, as I said, the homogeneous response or the transient part response, which is dependent on the natural frequency. This is the steady state response, which is also, of course, a function of natural frequency, but as well as the forcing frequency. This is the part that if you start the vibration with initial conditions, this would be 0, right? The project you did, right? If you consider basically a forcing function, right? You don't have to have any initial displacement or initial velocity so that the beam would vibrate. But if, for the project that you had, which was just a free vibration, you had to hit it, in other words, induce a velocity, or just displace it, let it go. So you need to have either an initial velocity or initial displacement or both to have this part. This one is not dependent on that. In other words, as long as you have a force on a system inducing a harmonic, basically forcing function, is going to continue to vibrate. So that's the, was it the third or the, yeah, the third observation. Next, we're going to look at more closely what happened to my, the fourth one, I don't want to miss out. That was the fourth one, no? Okay. No, for the fourth observation, okay, if the initial conditions are 0, okay, for the total response, okay, what will happen? In other words, let's say you have, this is the total response, okay? And you want to find A1 and A2. That's what basically you want. If you do that, I'm not going to go through all the detail of it because you have to take the substitute for time equal to 0. That gives you one equation in terms of A1 and A2. Then you take the derivative of the whole thing, substitute for t equal to 0, you get another equation, so you have two equations, two unknowns. If you do that and you evaluate it, you get A1 and A2, and the response as it would become this. Would have it this form, m omega n squared minus omega squared 1 over omega sine omega t minus 1 over omega n sine omega n t. So total response, if you start with 0 initial conditions, is of this form. Now we're going to look at something actually quite, yes,
Doesn't that conflict with observation two?
I'm sorry.
Does that not conflict with observation two, saying that the velocity is not equal to zero?
Does it conflict with this one?
Yeah.
No, we are assuming now, this is total response, right? And this total response, we want to evaluate the unknowns, the unknown quantity, these two unknowns, right? And the assumption we made, okay, let's say this response has started based on zero initial velocity. In other words, you have zero initial velocity, you induce a forcing function, let's find out what the total response is. That's what we
So
do.
it's-
You know, in general, this is the total response. So in order to find these two unknowns, you have the two initial conditions, substitute in here to find it.
So when is observation two true?
Oh, this is for the steady state response.
Okay,
only.
only for that.
Right, that's right. Sorry. So this is for steady state. I should have written it down. Okay. So if you do that, that's basically what you will end up with. Okay. So that's observation number 4. Now, let's look at this more closely, okay? I call that observation number 5. The amplitude of the oscillation was this, right? This is the amplitude of the steady state response. Okay. Let's take a look at this. Actually, I use F ball. Let's look at it much more closely. What is the numerator in this expression or this function? Isn't it this? If you had a static force, right, and the stiffness of this beam is K, would this not be the static displacement? So the numerator is the displacement of the system if the system was subjected to a force whose magnitude was equal to the amplitude of the forcing function. F0 bar is the amplitude of the forcing function. So if this forcing function was acting as a static force, it was not harmonic, had just this amplitude, that's what the displacement would be, right? What that means, right, is this, which is a very interesting observation. That means 1 over 1 minus r squared, right, is changing the static displacement, right, by this magnitude. So in other words, the maximum displacement, maximum dynamic displacement, because the steady state response is what? This is the amplitude times sine omega t. The maximum value of that dynamic displacement is this, right? So the relationship between the maximum dynamic displacement and the equivalent static displacement, in other words, if you had this, or if you had this, okay, is just this quantity. So if you can find the static displacement of the system, and the system now is acting vibrating under the action of a sinusoidal force, to find this displacement, just multiply that by this, okay? But what about this? The magnitude of this depends on the value of this frequency ratio. And there are 3 cases. Case 1 is what? case 1, we consider when R is equal to 1. Case 2, when R is less than 1, and case 3, when R is greater than 1. Okay? So let's look at all these cases. You have a force acting on a system, an undamped system, generates a response, which is this is, right? I've labeled that with double asterisk, okay? So this is the response of the system. What happens if the ratio of the forcing frequency to natural frequency is 1? Or in other words, what does that mean? The forcing frequency is equal to the natural frequency. So in that expression, maybe I should rewrite that, just because it's far, at least from where I see it. Okay, you have U is F0 omega times M times omega N squared minus omega squared, okay, times 1 minus omega N sine omega T minus 1 over omega, actually that's 1 over omega N sine omega N T, okay? So for the case that omega is equal to omega N, look what happens. You have 0 over 0, right? So you have 0 over 0, right? What does that mean? Now you have, again, to go after French mathematicians again. You know, they have just dominated the field of mathematics. Thanks to who? One of them. L'Hopital, right? Remember? You know that this is actually has a meaning. If you take the derivative of a numerator, derivative of the denominator, and then substitute this value, you will see that actually U will be of this form. You get F0 over 2K times sine omega N T minus T omega N cosine omega N T. If you plot that function, you will see it looks like this. You will see that the amplitude of this response grows linearly as time goes on, and in fact reaches the infinity. This is this phenomenon called resonance. So if you have an undamped system and the forcing frequency is very close or becomes equal to the natural frequency of the system, the amplitude basically goes to infinity, meaning that the system is destroyed, right? That's a very, very important phenomenon. I told you, did I tell you the story about this, of course we'll study this in underdamped systems as well, which is very similar to this. But did I tell you the story about Professor Newmark, one of the founding fathers of structural dynamics or earthquake engineering? Maybe it was in this section. Okay. This is, as you know, the situation you want to avoid. So if you have, let's say in the case of a structural system, if you are building building and you know that the dominant frequency of, say, the earthquake in that region, which is a forcing function, is going to be close to the natural frequency of your structure, obviously that's what happens. The structures are destroyed, right? So the story goes that Professor Newmark was hired as a consultant when they were building a Bank of America building in Mexico City. And he said it was okay with the design to be 42-story high. Everybody knew that that was a severe. Mexico City is one of the most severe earthquake-prone regions probably in the world. So many times the earthquake happened and thousands of people have died, especially in 1987, I think it was. That was the worst earthquake in the history of Mexico, one of the worst in the world. So everybody thought Newmark was crazy. So it came the earthquake of 1987. The entire downtown Mexico City, hundreds of dwellings, like anywhere from 1 to 2, 3-story building, just disappeared from the planet. They were just completely abolished. 20,000 people died. Bank of America survived. Maybe a few windows broke or something like that. The reason was he knew about the basically that earthquake region, what would be historically dominant frequency, and typically in a structure, for every floor, the period is about 0.1 seconds. So you have a 10-story building is about the natural period of that building is about 1 second. So for 42-story, you're talking about 4 seconds, and the period there was no more than about, say, I think 0.5 seconds or so. So it was way away, far away from the dominant frequency of the earthquake. Believe it or not, the locals thought that was an amazing miracle, act of God. So people started worshiping that building. That they thought it was a holy building or something. So that was a very interesting story. I was fortunate that when I was at the University of Illinois, Dr. Newmark was the department head. So that's the story that was told about him. But anyway, so Newmark contributed a lot to the field of structural dynamics. But anyway, case 2 is when you have R is less than 1, and case 3 is when R is greater than 1. Okay? So what happens? The forcing function is this form, right? The response is this, right? The steady state response you're talking about, right? So if R is less than 1, okay, if this is a forcing function, the response, in other words, if this is f of t, this is u of t, okay, would be in phase with the forcing function. As the amplitude of the forcing function grows, response also grows in the same direction. However, if R is greater than 1, this becomes negative. So this is for R less than 1. If R is greater than 1, then it would be completely out of phase with the forcing function. We'll see this in much more detail and what the physical significance or meaning is in depth. So let's focus on that, okay? So I'm going to call that, I lost track, was it the observation number 6? Okay. Again, going back to this amplitude of the steady state response. Okay. Since, as we noticed, this is the static displacement, right? As if a forcing function with a force, constant force with a magnitude that is equal to the amplitude of that dynamic force applied to the system. And this is what really magnifies that, okay? In other words, this is what magnifies that. We call this a magnification factor. But we use actually a different name for that, in general, since this is frequency dependent, okay, and it is this function that really tells us what happens to a system in basically under a harmonic load as compared with a static load, and is a function of frequency. We also call this frequency response function. You had a question?
The magnification factor, which thing that you circled is it? Is
No,
it the 1
this
over
is-
r squared or the
this-
entire thing?
this is-
Oh, the entire thing, okay.
Because that's what it does. This is really magnifies the static displacement, of course, depending on the value of R. It may actually reduce that as well, as we will see. But that is called frequency response function. We'll study that in much more detail. You will see that in the lab as well, okay? So now we are going to focus on,
Professor,
yes.
is the U of T, is that the displacement for the total response?
No, that's for the static, I'm sorry, for the steady state.
Okay, that's.
Steady state. Any other questions? So let's look at this frequency response function, because it's very, very interesting. If you plot that frequency response function, this is what you will see. Okay? First of all, we show this as this. Is a function that is a function of the frequency ratio. If you plot this, it looks like this. At R equal to 1, this is H, okay, this is R, okay? If you plot that, it would be, it looks like this. This is 1, this is 1, okay? And let's say this is, it goes like this. This is the square root 2. We're going to look at this frequency response function and really understand the physical significance of that next time. And we'll continue.